Everybody. My name is Enrique Anguiano-Vara, and I will teach in today some quantum algorithms that you have to know to start a bit into this field. The point of this is trying to, instead of going deep into the algorithms, the best way to learn these things is by trying to understand what we are doing rather than going deep into the matrix or into the physical or mathematical uh, premises. And the point of this, I think, is better to understand the general aspect of it, and I think for you is easier to understand. Also, by the end of this lecture, I will give you some extra information to be able to comprehend even better the points about these quantum algorithms. But the idea of this is more about trying to understand these concepts rather than going deep into that. And let's try to do some code. And yeah, let's do that together. That's the goal for today. So I think that right now it will be recording my screen. So now you will see the presentation that we're going to talk. So what's this? The idea of this algorithm, it will be divided by some sections. The first one will be some algorithms that they do not have any real applications, but it help us to be able to understand some topics. And the idea of this algorithm more about trying to explain those. It will be more trying to see the circuits and trying to comprehend better how that form of the circuits work. The other part will be the Grover's algorithm. That's an algorithm that is has plenty of applications. And after that, we're going to go through quantum Fourier transform, the quantum phase estimator. That this is, I think, the most important algorithm that we have here. And after that, the well-known source algorithm, the algorithm that breaks the actual cryptography. And by the end, we'll talk about Grover's algorithm again, because there's some special topic that normally a lot of literatures do not say anything about it, but I think it's really important to really understand what's the Grover algorithm. So, these are three algorithms that we're going to talk. The first one is the delta. The idea of this is not the best trying to explain the goal of it, but I think it's better to go through this part over here instead of trying first of all to trying to understand at first glance all. I think the best part right now will be understanding what is qubits and what we're doing here in its step. Okay, so by the previous lecture that we have some Pauli case, some 1 qubit case. The idea of this is like you have a sphere that is a qubit, which will represent a point of that sphere. Okay, and which each operation, unitary operations, we can perform some rotation to that vector inside of that sphere. That's the point of each output that we perform. It will be represented by that. And knowing how to play with that vector gives us that advantage that we have between classical computing. So, the first of all is the Hadamard gate that we have here, which represents a superposition. The idea of this is like we measure on some basis that we established. So normally it will be the basis of 0 and 1. And the idea is that you can put the vector in the middle of those. So the probability that it will collapse, like thing like, I don't know, like you have this book So the probability of collapsing will be half on left and half on right. It could not be like here and be like oh. But the idea of this is like we can perform the probability, and applying the probability help us to perform these calculations. So here we're gonna perform of all n qubits n Hadamard gate, that is just a bunch of Hadamard one upon each other, like not having any correlation between each other. But this is like the normal notation to be able to understand this. And in the one gate, we'll perform a Hadamard gate here. Okay. After that, we're gonna perform some oracle, that is a function, is a sort of more complex rotational gates, which can perform an output that in this case will resolve the delta algorithm. And again, we will like build the part about that Hamiltonian, that Hadamard, that we make that superposition. Note that all operations are unitary, and that means that if we have two, for example, X gates, Hadamard gates, whatever, any gate that is here, also complex, well, complex no, but if we perform two times, like one in front of each other, nothing inside, one from each other, it will compute nothing. And that's because the matrices will perform like the identity of that two operations. That's the point that we call these operations, these oracles, unitary, these operators. For more complex, the idea of this is trying to do the inverse of that. So we will do the the opposite order that we used to do this oracle. So for example, if we have a Hadamard X C gate, to perform the identity, we will go like again, a C gate, an X gate, and a Hadamard. Okay. I think this is like the first step. I hope like this is making sense. And I think that that's the first step that we need to do. So, yep. Everything good right here? I'm gonna wait for a sec. Like, I don't know if you can type something here. If not, I'm gonna continue because they don't tell me that I'm not mute. Okay. Okay, I'm audible. And again, as well, it's like this is. I hope the thing that I just said makes some sense. So going back on this, the idea of the Dot's algorithm is to determine whether the function is constant or balanced with a few possible iterations. The point of this is of what's constant and what's balanced means like for each function, it could be or all zeros or all ones, independent of what's the output, or half zeros or half ones. The point of the classical performance here, I think, is this form is in form of bits. It will be exponential and quantum will be constant due to the perform that we may have with the Hadamard gates. We apply superposition and therefore we can have this. So these are also different type of problems with the same idea. In general, form that it does not have real purpose, but it is good for explaining. But if we apply, and you have to understand a bit of the Dot's algorithm, I think these algorithms are the same, one from each other. And I'll give you later the presentation, so if you want to research more. But I don't think there's a need for that. So I think that it's better now to explain the Grover's algorithm. Now, this part, everything that we're gonna tell is have some purpose about it. So I think that's the best part. So Grover's algorithm is an algorithm, it's a search algorithm. So normally in iterative search, in classical computing, we'll have the iterative search will correspond to a worst case scenario of n elements. The idea of this is you have n elements, one from each other. The worst case scenario will be always trying to find that last element that you're finding for. So therefore, we apply this notation to be able to understand what's the worst case here. In terms about all other classical algorithms will be the binary search, which performs this in logarithm time, but we need to have the array sorted. Here in quantum computing, we have the Grover's algorithm that without the need of being this array sorted, we can search the element in square of n. So therefore, we have a quadratic speedup for finding an element. And the best way to understand this, instead of going directly to the slide, is trying to understand that Grover's algorithm is like a slingshot maneuver. In Spanish, for the people that don't know what slingshot, tirachinas. The point of this is let be a W the state that we try to find. And let's say we have a bunch of data, an array that is going to be A, that in this case, in this particular case, let's go from 0 to n minus 1, like the states. And we will have only one state that matches W in A. Okay? Given this, we could start in this part, which represents the uniformal superposition, because we're going to apply a bunch of Hadamard gates at the start. And the idea of this slingshot maneuver is trying, first of all, loading this slingshot and later launch it. So how do we perform this operation? Because we have two operations, therefore we have to load and we have to shoot. In terms about loading it, we can flip the phase. So think about that sphere that we have. The idea is trying to flip flip the amplitude. That's the idea of W if it matches, and if not, we're gonna stay the same. So therefore, we apply this operator right here that applies that load. And when we're trying to suit it, it will be the Grover diffusion, that is this part of here that is not need to you to understand what's going on in this part, but it represents that, well, I think this is inverted, but no, because we're using Qiskit. But the point of this is like we're gonna apply the by the mean of the amplitudes, we're gonna apply the symmetrical output for it. So let's say we have this as a mean, okay, and we have some upper amplitudes that we didn't change because in this case it's the first iteration, so it will be on the same amplitude, it will be equal, and later we have some different W amplitude that will be the same value by negative. So therefore the mean of that will be like really near but positive. It will be really near to 0, but it will be positive. Therefore, when we can apply that symmetrical value, all the equal probabilities that we have, it will go again the same, but in the negative form, because it will perform the symmetrical value. But the difference is that W that we have as is for, well, indeed, for all the symmetrical will be less amplitude because it will be near 0, but it will be in a bit positive. Sorry, it will not be equal. And for the W, there's a long distance between each other. It will perform a higher amplitude than we had before. So therefore, we apply at iterations that we perform a near state to W. Given this a bunch of iterations, we can perform an algorithm that goes through that W that we were asking for. Okay, that's the graph algorithm. That's what we normally do, and given this, I think that we repeat a number of times. But what's that number of times? Okay, so in normal literature, you'll find something like this. P divided by 4 of a square of m times. But this is not technically correct. There's another parameter, that is m, that we didn't talk about it, because we assume there's only one state in this array. So if we have more states that can be this output, for example, let's have an array of all the elements of 3 qubits, and we want to find the elements that ends up by 0 and 1. Therefore, there are two possible outputs, the 101 and the 001. As we are doing a number of iterations, if we do not think about this, we will perform a bad output, and I think it's a really bad output if we did not think about changing the number of iterations. Because note that this is is not like a perfect algorithm, as if we go beyond the number of iterations, it will be a really bad output. So we need that parameter m to know how many elements are in this array. And this will be part of the second section we made for the Grover's algorithm, that is called the quantum counting algorithm, which this algorithm, the idea of this is, before applying Grover's algorithm, let's try to find how many elements matches W. So, for instance, you may think that this is a bit contradictory, but in quantum computing makes sense. And by the next sections, you will see how can we do this. So, the quantum Fourier transform. Again, we are not going too deep in this idea. It will be easier for understand that in quantum computing, the idea is, instead of going through a classical form, let's try to apply this quantum advantage. For example, the big idea is trying to encode integers efficiently, not just in a computational basis as simple bits. For example, we here add the form of this classical form that we technically can use, but it will not give us that speed up that we want. So what do we do? The idea is simple. For example, here we have 4 qubits. We're gonna apply some specific rotations. Again, for example, the idea of the Grover algorithm, that we see that in a 2D form, we can see this again, as each form will be performed a specific degree of calculations, and the form of all of these we can get back to this original world to know what's the value. So note that this you can get easily any value, because collapsing the state from 0 and 1, given that 100% of the state will be 0, that's easy. But note that if we only have one qubit with one output, one vector, it will be harder for us to be able to know what's the value, because it will have not like that exact probability. And the idea of this to work efficiently will be applying some rotational gates and later applying the same rotational gate but with a different form. In this case, what I mean is, like, for this we apply a 16th of an amplitude, so for a rotational gate. But here is 1/8, 1/4, and a half. The idea of this is that given this set of rotational gates, we can perform into this frequency world, that is the Fourier transform, makes that operation that enhances this speed up for quantum computing, and later we can go again through this original world with that data. Okay, that's everything that is said here. As well, you have some mathematical proofs, and later the bad thing is that that's in Spanish, but I mean that's mathematics, so you can understand that. And yeah, and that's the idea, and therefore we apply some rotational gate that here the k represents the qubit, as you might see, like the reason why do we do these specific rotational gates. And now, given this explanation, you have to say, okay, but what operations essentially do we speed up? Okay, so we have some of them as addition, multiplication, but the two most important here right now will be defining periodicity and the modular arithmetic. Given these factors, that's the reason why we say that quantum computing breaks RSA. And in clickbait, it will be like quantum computing breaks cryptography, but in reality, it only breaks this algorithm. But in classical form, this cannot be done because it will be not polynomial, but now we can perform with this change a polynomial version that could resolve it. So before going through that algorithm, that is the source algorithm, I think it's better to go through the quantum phase estimator that indeed uses the source algorithm inside of it. This part as well, this is I think the most important algorithm from all that we're gonna try to talk about. And the idea is trying, because, well, it's really important because it's really general and it can be performed in a lot of different applications. For example, in my next lecture for tomorrow, we'll talk as well with this algorithm as it can perform the output that we want to have. The main idea, well, this will be like way better explained for the next lecture, but the idea is that we can perform again that quantum Fourier transform that we saw before. So therefore, we can resolve, like by a value, by a eigenstate, complex, like a complex task by giving an operator u. And that's the point. So we want to estimate this phase that we have right here efficiently using a quantum computer. The idea is the output, to be honest, will be more that value, the eigenvalue, or in this case, that element right here. So as you can see, this form is the same as this form. So you may see that we normally gonna use, well, it's a rotational gate, and we're gonna use a rotational gate to be able to perform these calculations. So the first step is the estimation qubits have the Hadamard operations again to perform a uniform superposition. So bands of Hadamards, one from each other. The second step, the gold qubits apply a control U operations. Again, a control U operation from the first lecture is just conditionals. If this happens, then do this block. That's what's going on. It's combined with estimation qubits. Its pointer, so it rotates according to the hidden frequency of the target, the one we explained in the quantum Fourier transform, encoding finer details of that amplitude. Well, sorry, of that angle, not amplitude. Yeah, so therefore we just set a bunch of rotational gates, and after that we can perform the inverse of the quantum Fourier transform, as I said at the start of this lecture, applying the opposite gates that we apply in one form. If we do that inverse and then we apply again, we can get an identity matrix, or in this case, as we perform some changes, we can perform here the output from the quantum Fourier transform world to a real world. And this is the idea. So you may see this algorithm as a bit abstract because we didn't set how can it be implemented, but know that this phase estimator, that is really what this means, like it finds that angle that we talked before. It has a lot of applications, but for example, for quantum machine learning, from quantum chemistry, like quantum chemistry, I think is the main algorithm, like theoretically the main algorithm, and all the remaining algorithms based on this. And for example, from a quantum algorithms for linear system of equations, a quantum counting algorithm, and that's also the part 2 of the global algorithm. So note that all of these applications will be more visible later. Right now it's a bit abstract, but you'll get the idea of why do we perform this rotational gate. Again, if you have some questions, man, later we can talk about this, and I'll be happy to talk more about these concepts. So, yeah, and also this part will be very explained in the quantum chemistry, not because here I cannot explain that, I think because the topic makes that easier to understand. Okay, later there's a source algorithm. This part I really like to talk a bit less about it and give you more those elements, like the extra materials, because I think the source algorithm is better to see, like all the proofs, all the things going on. But we can try here. So the problem to solve is given an odd composite number n finds its integer prime factors. Again, this is the reason why we do this is because we want to break RSA. That's the algorithm. So, and this is one of the first algorithms you know that it makes this quantum advantage. Indeed, I think Google, like talking about this quantum advantage, just said a couple of days before that they have implemented an algorithm that actually demonstrates this quantum advantage. There's a difference between demonstrates in terms about experimental than theoretical. So this algorithm is theoretical right now because we don't have enough qubits, enough hardware to be able to perform these things. But we know, given that theoretical point of view, that this will work in the future. Again, as we will need in this case for be able to perform these algorithms, millions of qubits to be able to compute with the RSA of 256, for example. Again, this is the same as the quantum phase estimator. But this is some of some specific algorithms that you will need like more qubits. And there's other algorithms that help you to have the same approach, but in a different way and a bit less efficient. But you have less qubits, and therefore it's you can actually work with these algorithms. But that will be for the next lecture of tomorrow. So the point of the source algorithm, the idea, is, well, there's a classical reduction that the first part we're gonna pick a random number, and later we're gonna compute the greatest common divisor from A of n. And again, this is all the things that we're gonna talk about, but I think it's better here to let you read this because I think it's really good explained by Arianna. And I think, yeah, so I'll give you this part of the presentation for you. But the idea is applying this quantum phase estimator. So now we can represent the operation of multiplying this A modulus n. How can we do this? Okay, we can apply again that rotational gate and saying, okay, n is gonna be this. So A modulus n will be this phase. That we can say, okay, 57 modulus 2. Okay, we can think this about having a sphere. So this is 0 and this is 1 of the model 2. So 57 will be like doing a lot of spins, but later we end up by this value of 1. That's the idea. And given this angle, we can like we can have again those values that RSA normally applies and said that this is efficient in terms about security and it cannot be breakable at the time. But now using this concept of the quantum phase estimator, we can have that output and break this algorithm. And that's the reason why the source algorithm and indeed more the quantum phase estimator can break this algorithm. Again, I think that's again the same form, the same way that we talked about before about that specific form about these rotational gates, and it's the same. In this case, the operator that is U, that is the one that are right here, will perform an operator that is this part. Okay. And well, after that, we will have some result that will be this K, and that has this type of output, and later by dividing this part, I think this is like not okay, well, whatever, by dividing this factor, we can have a decimal approximation of these two values. Yeah, so that's the angle that we were trying to find. After that, after the quantum circuit runs, we get a number that is related to the period of the function, that rotational gate. Gate no, that rotational angle. However, that the quantum computer gives us only approximation of this, which is close, but we try to find that error. So we use a continuous fraction algorithm, this algorithm that is like on the right. It takes its decimal number we measure from the quantum computer and finds the best fraction that matches, meaning it gives us the integers b and c such that is more or less the same. But sometimes this first fraction doesn't give the exact error because some fractions might be missing. So we can run a quantum part several times, each time getting new fractions. And given this bunch of b and c, for example, we can apply the least common multiple of all the denominations and give us the period error with high probability. Indeed, there's a code in the association behind this Wolfes is an association about STEM research and cognitive programming. And in terms of cognitive programming, I think there's an algorithm, well, there's a problem that talks about given 3 queries. Let's try to find these values of B and C. Well, this is just fun, and later you can see that everything at this node, like part indeed of only quantum computing, can be thinkable in other aspects. So the point now is that if we know R, we can compute this really common divisor, and later we can have the non-trivial factors of this n. So this step connects with the quantum part and the classical part of the source algorithm, computing this factorization process. So given all these data, and now you can maybe receive this a bit more. Given all this form, we can perform that n value that we will try to find, and it was hashed by the RSA, and the source algorithm reverse that. This part will be also have some extra notes with it, because I think it's better for you to be step by step. In this case, it's better trying to see the mathematical proof rather than doing like pseudo algorithm. But for this explanation, I think it's better have like a brief idea about, okay, so therefore the source algorithm applies some quantum phase estimator, and after that, given that angle, we could get some approximations. I mean, that's approximations in different type of shots. We can get that R, which we can get that n value. That's the main idea of it. And the last part, going back to it, it will be the Grover's algorithm. Again, in this case, the part 2. And the idea of this is, again, applying this quantum phase estimator that we now, right now, we know what's going on with this. And now we can apply that thing that we said before, like trying to find the number of element that matches that W in that array. So in this case, we can consider again this unordered array. In this case, this part. And now let's be W a substate with k qubits that is obviously lower than the array that we're trying to find, or maybe equal, that represents mark. Therefore, there exists an X that contains W as a subresistor that if exists such a Y, we have that operation. That this is mean like if you have, for example, all these states that start with 1 in a span of all the elements that have 3 qubits, therefore Y will be all the elements that have 2 qubits. And that's the point. So the idea here is you connect like 1 qubit to each other. That's the representation of it. Indeed, the correct form is called the tensor, and that for each element in the matrix you multiply inside of the matrix. I think it was explained in the previous notes that I sent from the extra things for yesterday. But again, let's go. Let's continue. And now let's try to have a B that is gonna be contained in this A of n. So this one. So this is the same thing that we said before. Let's try to find all the possible values which represents this W. And that's the idea. Now we have a different form. So let f again be the same function, but now it wouldn't be like if W is the same as X. Now is if X is contained in this subspace, that we are trying to find this by the quantum phase estimator. That's the idea. Okay, and given that we have that M, and if we have that M, therefore we can apply the number of iterations from the Gorbel's algorithm, and we can find that elements. Note again, we also do this because remember that given any state, like if it's 1, 2, or 50 qubits, all the probabilities need to sum to 1, if they are correlated, of course. So therefore, if we apply it first time as a proposition and later we apply some gates and we measure of them, we will have an output which, well, later we'll have an output, but before that we will have such probabilities that again all of that sums 1. We have that factor, again we also need that M to be able to not like well, as we have that, we need that M, so we can perform that amplitude specifically for that values. But again, it wouldn't be 100% this one state, well, of all. Sorry, it wouldn't be like 100% of all the states that we're trying to find here in B, because that's not possible, because you are performing by the theoretical point of view that all the sum of all the amplitudes, well, the sum of all the probabilities that are the absolute value square of the amplitude will be equal to 1. So therefore we'll have like a really good amplitude to search, to be able to search these states, but it wouldn't be 1 if we have more than if we have an M greater than 1. And that's it. And again, the idea is the same. We're gonna apply a superposition, and later we're gonna apply a Grover operation. So in this case, the Grover operation I think is here, and we're gonna apply that Grover operations unified by that form of the quantum Fourier transform, so we can get the output that we want. Again, but that angle. And that's it. Well, This idea is that this speak will be recorded, but I had the exam today, so I have a lot of time and I really have some good feeling, for doing this. I want to change, like, I want to do it. And yeah, so now if you have any questions, I'll be back on Discord. And if you want to try to code with me some algorithms, we can try to do it and be able to start knowing a bit more about this. So, any question that you have in mind that you want to talk about, any things that you still don't understand, and I'll be here to talk to you. If not, just like make an emoji or something like that to be able to know that you are understanding this. Okay, so I guess there are no questions.